All right, Luann, go ahead and get started.
Thank you, Harvey, and welcome everyone. I feel privileged to be able to take Gary's place at the 11th hour today, and he will be in our thoughts. And as we've talked about, he's fine. So we're really lucky today to have a professor at the College of Marin. You know, when ESCOM is so much a part of the college, and it's so great for us to meet and meet other people that are at this college and find out what the research is and what the faculty are talking about and what the students are learning. So to have a professor is particularly an important thing, I think, when we do these spotlights. So today we have Paul Daubernmire, and I'm very happy to introduce him. I do have a bit of a bio from him, and not having had a chance to go over it in advance, I'd like to read it. And it's not too long, but it just tells you more about him than I might have been able to do by what I've learned online. He joined the College of Marin Chemistry Department in 2017. His interest in science education was cultivated when he completed his teaching credential in Boston area public schools while a Harvard undergraduate. After grounding himself by attending seminary and working in laboratory safety design, he began a teaching trajectory that led to the community college and university levels. Through earning his master's in polymer chemistry at Georgia Tech and his doctorate in science and math education at UC Berkeley, he increased his repertoire of chemistry, curriculum, and pedagogy. Having enjoyed the privilege of engaging and exciting science instructors through high school and college, he's always looking for opportunities to encourage good students to be STEM curious. He takes great pride in mentoring his 3 sons to be diligent, continuously goal-oriented, and people-serving. So he's got a great background. He's also was at the Lawrence Hall of Science at Berkeley, and just has a really interesting background. So I welcome you all and express our appreciation to Paul. Well, you can take it over, Paul.
Thank you for that really kind introduction, Luann. I'm really privileged to be here with you all this morning. This is the fruit of a conversation that started last spring with a number of the ESCOM officers, and I'm glad that we finally were able to make it happen. As Luann mentioned, I've been involved in the STEM trajectory, and I'm going to open some slides up and make sure I have things shared properly here so that we can kind of, let's see.
Yeah, just make sure you click the share video button.
Perfect. Okay. So this, I don't want it to take over my whole screen. So let's see if I can do it this way. 1 second.
Well, there you go.
Okay. Are you seeing just my slides, or are you also seeing?
Switched it over to your presentation view. You'll have to swap displays there. There you go.
Okay, perfect. Unfortunately, I've lost the visibility to see my audience, which as a faculty member is everything. So I'm going to do one more little thing here to see if I can pull your all screen back up. Okay, so as Luann mentioned earlier, I'm going to maybe treat this as a little bit more of a conversation than as just a talk. And with that kind of background, I'd just like to point out, for some of you, maybe this acronym STEM just needs a little clarification. It's been used widely now to kind of encompass 4 fields that have been lumped together: science, technology, engineering, and mathematics. And some have come across an acronym STEAM, which also includes arts in there. And that often is seen in the K through 12 level. But as we go up to the college level, typically the A gets less incorporated because the coursework and the trajectory you take to be in one of these disciplines is more closely unified in those 4 letters you see there of STEM. So in today's presentation, I just want to walk a little bit through, and let's see again. I think I may have.
No, it looks good right now.
Oh, it does.
Yeah,
Okay,
but
perfect.
you can go to full your slideshow, but
And the slides are still visible to you all?
well, we're seeing your whole PowerPoint there.
Yeah, I'm sorry for the small technical difficulty here.
Well, it's hard when you're on a smaller screen too.
Let's see if I do this and press that button.
Now, there, no, you went back.
Swap displays again.
There you go.
Okay, perfect. Well, let's do it like this.
It
So
keeps,
just as a little outline of our presentation, I wanted to tell you a little bit about a class that I teach and allow you to experience a little of that class. It's called The Magic of Chemistry. And then go on and describe how that course and other experiences at COM led me to apply for and receive a grant from the California Education Learning Lab to work on different aspects of this STEM trajectory here at COM, and then bring us all the way into spring of 2023, where we have some initiatives I'd like to share with you all that there's even entry points for current ESCOM members to participate in. So just to begin with, I'm going to show this little video, and I don't know if I did enable the audio. Perfect. Okay, so this is a little video that I often play or reproduce for my students. Okay, let's get it going. You got your apps ready, your 10-second timer. I'm killing it. Come on. Need to do bots and matches here. There we go. Whoa. So there's a couple things happening there. One is there's something seemingly invisible that's undergoing a change to produce a lot of light and energy and heat. If you're in the room, you actually could feel a fireball. And second, you catch me there at the end. I'm already diminishing in the amount of hair my head keeps, but I've managed to singe some off as well. So one of the kind of comical ways that I help students remember my name Daubernmire is that it's alliterative or rhymes with hair on fire. And so when you cross paths with me, you can see how the hair is doing, what I burned off recently. So how we often start this class is with a question, and I'd like to pose this question to you all. So as Luann mentioned, and as Harvey pointed to the chat, we'd like this to be an interactive process. So this first question, let's see here, is what do scientists do? And if you could type a sentence or a phrase into your chat box, or if that becomes a difficulty and you just would like to raise your hand and chime in. Again, I'm not looking for a textbook answer. I'm looking for your either lived experience or your thought as to what scientists do. And this is how we often start our class with our young students. So we're getting some contributions already. Investigate, study the unknown, test theories. Scientists explore the known in order to contemplate and define the unknown. Oh, here they come. Ask questions. Try to solve the mysteries of the world and apply them. Help us understand the invisible and how things function. Hypothesize, figure out things, research what we don't know, test. You can imagine a room of 28 students, right? I have them pair up and the room just starts buzzing with these little topics, just as you all are doing the same. And the answer I give, while all of these are correct, is I point to Newton. And I point out that this famous quote of his, who basically brought us the theory of gravity, as the story goes, right? He's sitting under a tree, maybe an apple tree in Cambridge, and an apple fell, and he had to hypothesize about this and test out theories. And eventually, at some point in here, he had to make a bold guess. And this quote I really love, that no great discovery was ever made without a bold guess. And so that means often putting even that word guess implies that there's some uncertainty there. There's something that we don't know, but the boldness comes from what we do know. And so we take what we do know and inform our uncertain conjecture or putting our step forward. And isn't that life sometimes, right? And what I like to do then is turn this conversation to help students recognize that every one of us has been a scientist at some point, and every one of us has the capacity innately to be a scientist. And that maybe we talk later about obstacles or barriers or things that maybe have limited our opportunity to do so. But this idea of having a bold guess is crucial for us to be scientists. And so then I turn the course in a different direction. It's a humanities course. This is Humanities 101. So I actually bring it to the historical point of asking students, where did the study of chemistry originate? And I'd like you to just maybe put in the chat again. Imagine you're sitting there with a partner or two and you're kind of having a conversation. Maybe you would want to name a country or a continent or a period of time or a name, right? There's multiple entry points here. I'll give you a minute to throw your ideas in. Okay, so the feed folks are contributing prehistory, Pro-Magnum Man, alchemy, cooking, fire, medicinal plant exploration. In Persia in 943, that one's very curiously specific. Like to follow up on that one. European medicine, noticing changes such as autumn leaves, Neanderthal man, right? So we may viewing the skies. So all of these are, again, bold guesses, and I appreciate everyone kind of throwing out their ideas. And I'm going to turn us to a particular lens that's not represented in the history books. I noticed nobody said 1803 John Dalton. So at least we're open-minded to recognize that probably chemistry started earlier than then, and to actually kind of take this in a certain direction. I'm going to bring us to a map of Africa. And believe it or not, we're going to zoom in on the fertile Nile Valley. And we recognize, because of the flowing of this fresh water downstream, there's able to be a whole population that originated. And that population ultimately attributed something to their development and progress. And the word comet or kemet is the Egyptian word for black. And black was indicative of the rich soil that they noticed, that when they planted in the black soil, their crops were richer and produced more than when they planted in other soil. And so we came out eventually with a word that is the origin of the word chemistry. For those linguists here, you can see the root there, alchemia. And someone in the chat actually mentioned alchemy. And so that origin of alchemy, we'll see later, was a study of trying to take substances and turn them into gold, and a larger kind of world philosophy and outlook of mixing different elemental principles to make a change in substances. But just the origin, even agricultural and societal and cultural, around the word soil, right? Black soil was the beginning of the study of this first field that we now associate with chemistry. And so when we're working with students, this obviously kind of blows their mind, because this is not something that's documented so well in our modern textbooks. So, oh, the slides didn't pop up here, but maybe I can point to now the first documented chemist. And this, of course, is a representation of her, Taputi Balatakalem, who was a female overseer of a palace, and in 1200 BC in Babylonian Mesopotamia was documented as a perfume maker. And so that's our first chronicled, recorded chemist. Not just someone, of course, playing with fire or just cooking, but actually systematically working with the extracts and essences of oils, calamus, a particular type of reed, and cypress, myrrh, and balsam, these fragrant aromatic oils. And then also documenting the process of distilling them, filtering them. And this is the oldest referenced distillery in all of our history. I want to actually pause right here. I have a little video, and I feel might be appropriate to, I'm going to stop the slides and bring in the video here. I wasn't planning to show it originally, but I think in this context, it's going to share something that's quite eye-opening. And even when I say distillery or still, we might have some concepts about that, but I wanted to point out how a modern day process is taking advantage of that process she discovered millennia ago. So this is a little video on the process of steam distillation, and you'll see some applications to it to even today.
How steam distillation works. Most essential oils are produced by steam distillation. Steam distillation was invented around 1000 AD by Persian alchemist and healer Avicenna. It has been practiced for thousands of years since then, and is still one of the best ways to take freshly harvested or dried plants and extract pure essential oil. Take a look at this distilling apparatus. The bottom reservoir is filled with distilled water. Above is an alembic chamber that holds the plant material, often called biomass. The biomass is full of tiny sacs that contain essential oil. When the water boils, the steam passes up into the chamber. As the steam passes through the biomass, the temperature causes the tiny sacs to burst open, releasing the essential oil. The essential oil rises up with the steam, and together the oil and steam pass into a tube. This tube passes through a cold condensing chamber. The cold temperature changes the steam back into liquid, which drips out of the tube. The liquid collects in a new reservoir, where the water and oil separate naturally. The water, which is called hydrosol, is left at the bottom, while the oil rises to the top. And lastly, the essential oil can now be collected and bottled.
Okay, so that little video, though it's sharing about steam distillation made by an aromatherapy company, you can actually see has quite a few applications. If we were to talk about things such as distilling alcohol, in the last 10 years, there's been a big movement to extract some of the some of the bio oils that are found in the marijuana plant, so cannabis-based industries. Of course, the aromatherapy that's mentioned here. And actually, if you are working with any medicinal extract, right, for our aches and pains, it was collected in this kind of a process. So it's quite neat that it's actually just basically taking water and heating it up and passing it through some biomass and then collecting the oil that passes through. And so I often use the experience of those who have worked in kitchens and just worked with changing the temperature of water to make processes happen, to show how you've actually been a chemist for many different experiences in your life, but no one's ever pointed it out to you. So some of our students who are a little older and have been drinking or imbibing can talk about the various types of proof, and we can use that to begin to talk about alcohol levels and how you can separate the alcohol from water to make a stronger and stronger drink. And maybe I'll just jump over to the slides again for the kind of historically and linguistically oriented. Even the word alcohol is kind of an interesting origin. There's some debate where originally it in the etymology of it, but the origin is definitely Arabic. And it either comes from an origin of alcohol, which is a type of powdered version of antimony, an element used in a cosmetic, or alcohol, which you can see has an origin of the effect of drinking too much alcohol, that there's a demon or a spirit that's unleashed. So we have that English word ghoul that we still use today that comes from that origin. So there's quite a bit of interesting science and humanities that are built up in the STEM learning process that I pull from to engage our students to motivate them sometimes to get through the numbers and the chemical symbols that kind of run together. By giving them these stories and giving them these applications, it allows their natural curiosity to kind of run with things. And so eventually we get to John Dalton. And again, I mentioned him earlier. He's called the father of modern chemistry. And he was the first one to propose that there are tiny invisible spheres that make up everything. And this was an idea that was picked up on by Democritus back in the Greek BC era. But Dalton was the one who really documented it in the modern day. And for the last 200 years, we've run with it and built off of it. And there you can see kind of an early model where he just tried to say this thing is different than another thing, and he didn't have ways to document it. So he did what we would have done, is make different notches or different shading to differentiate the color of one object from another. And so you can see how, again, the early sciences are wrapped up with art and representing your ideas on paper, so that your communication, the communication of your idea to another person, is effectively carried out. And again, many of our students as scientists, they don't value, or they haven't been helped to value, this aspect of being a scientist. So then I'm going to bring it to maybe a little bit more of a technical definition. And maybe with your kids or your grandkids, you stepped on one of these late at night and barefoot. It's happening to me all the time. You found some of these Legos, these individual building blocks. And I like to use this as an analogy. If we called this an atom, that's that tiny, invisible, indivisible particle, right? But chemistry tells us the whole world is made up of these little atoms, these spheres that are represented by this little Lego block. And if we could take one of these blocks that has a certain type of characteristic and combine it with another block, then we're going to make a molecule. So it's a combination of two or more atoms. You can see here we kind of put together a water molecule, which is H2O. We're familiar with that. That's been built into our vocabulary. The salt that you season your food with, as well as the salt that you taste in the ocean air, is the same salt. It's NaCl, sodium chloride. And that's two other atoms that are just linked together as a molecule. So every substance is made up of atoms, and depending on the combination of the atoms, it changes the properties, and it changes what we experience when we go to contact different types of material. So I'm going to bring us, maybe to this slide real quick. So this was actually research done, you can see, about 10 years ago at UC Berkeley. And I keep saying invisible, and this has been the cutting edge of research. Is it possible to make these invisible atoms visible? And what I'll show you is that in the last about 10 years ago, so we've advanced since then, through a particular type of imaging technique, we can actually begin to distinguish a molecule that looks like this one down here on the bottom through imaging techniques to visualize the pattern, and actually even the orientation of the atoms in the molecule, to distinguish between the reactant and the product, the thing you started with and the thing you ended up with. And you can see how the lighting pattern and eventually the imaging pattern is distinct. And we're right there at the threshold of being able to visualize what had been for thousands of years invisible. So this is really cool for us chemists, that we now have these little techniques that are getting us closer and closer to confirming that what we're seeing is actually what we've been hypothesizing that we would see. So I'm going to zoom back out. That's real down in this level that we previously had to use our imaginations for, and now we can begin to actually visualize these atoms. And I'm going to bring us to something a little bit more experiential. And I'd like to open up the chat again and ask this question: what does this tag have to do with invisible particles? So you may not have seen this exact tag, but you've definitely seen this under penalty of law, this tag not to be removed except by the consumer. I'd like you to consider, let's find the chat again. See if any folks have any ideas. What might a tag on a pillow or a couch or a mattress? Right, Harvey said we were afraid to remove the tag when we were younger. I'll have a statement for you at the end of this that can relieve you of that. Was flammability. Again, the tag seems to be telling us something about the composition here. Gilda's adding see and feel the materials made of foam and rayon, right on from these names here. Okay, here come a few more potential allergens, but there's foreign articles that could seep out. Right, but we don't see these atoms. And so I'm going to bring this tag to what we associate. Let's see if this is advancing. Sorry, my slides. Okay, so I'm going to bring it again to the mattresses, and that tag, or these particular tags, originated through some federal regulation in the early part of the 20th century. It was, believe it or not, no regulation as to what went into mattresses. And so what it takes to make a mattress, there you can see cotton and it's packed in a certain kind of a layer. But back in the 1900s and 1910s, mattresses were being filled by Scrooges and penny pinching factory owners, and they would take whatever they could, whatever stuffing material was available to them at a cheap cost, and go ahead and insert it into those mattresses. And so there's stories of used clothing, used blankets, even of discovery of corn cobs, basically all kinds of things just stuffed into mattresses for padding. And as a result of that, you ended up having disease get spread, right? If you can imagine someone with illness and their clothes is now being put into a mattress, now you're propagating this. So the federal government came in and regulated, and basically those tags were instituted as a result of this kind of needing to clear up the actual substances that are being put in. And now they've taken on a life of their own, and they instill fear into us that we're not going to even remove the tag. Well, I'm here to announce the consumer, which is you, the purchaser, is allowed freely to remove that tag. It serves no purpose to us, the consumers. It's actually a warning. It's a slap on the wrist to the manufacturer to make sure that they're not putting any substances in that shouldn't be in there. By the time we consume it, one of my sons has this little stuffed animal with a tag. There's no reason to have that tag on a stuffed animal these days. But you can imagine 100 years ago, you might not have been clear as to what was being put in. And so I just, again, use this to connect science with the legal side or the regulatory side of interacting with society. In order to know how to write a law or to identify a rayon or a foam, you need that scientific background. Even if you don't go on and become a practicing scientist, you need to be able to communicate intelligibly and clearly to set those standards. And so I'm going to bring us now to another video. I'm going to switch gears real quick. And this video actually is going to give us a little bit of an insight into that material that was listed on that particular tag. It said foam and rayon. And so I'm going to share a video here with that was made by a production team at UC Berkeley. I was able to be a little part of the work here. And we had a well-loved laboratory technician, Lonnie here, who recorded a number of videos for us that are now saved through the College of Chemistry at UC Berkeley, and really give us insight into some experiments that we never could do at home. But because they're available to us, we can actually reproduce those for our students. So I'm going to play this video, and I want you to, as you watch, think about the invisible things being made visible, which is one of our magic tricks in chemistry.
Polymerization is the process where smaller molecules, called monomers, link together to form long molecules, long chains called polymers. Polymerization is the process of those monomers forming long chains. Now, the chains of molecules can be extraordinarily long. In fact, you can make essentially indefinitely long chains of molecules. And Lonnie's preparing that here. He's mixing sebaceous chloride in carbon tetrachloride with hexamethyldiamine in water. Those two solutions don't mix, but at the interface between them, the molecules combine to form a polymer. And Lonnie can actually reach in and grab the forming molecules and pull them out in a long chain. The molecules will continue to polymerize. So as he draws the molecules out of solution, the final product, the monomers continue to react at the interface and form more polymer. In this way, he can make a long strand of nylon, a synthetic polymer. Here you can see the nylon forming at the interface between the liquid layers. Nylon is an important commercial material because it can be used to form fabrics. And it revolutionized the fabric industry because nylon is cheap and easy to make and can replace cotton and natural fibers in clothing and other products.
All right, so that particular video gets the students really thinking, right? Because it appears to be a clear, colorless little vat, and suddenly out of nowhere, this thread is forming. And then once they're told that this can connect to clothing, oh my goodness, right? What else gets made out of these kind of clear and invisible kind of substances? And so, again, bringing it kind of historically back to Wallace Carruthers, who was actually a researcher at Harvard, and this was accidentally discovered. I have a couple pictures here where we can understand that. Okay, so there's Carruthers, and there's the scientists are trying out the material. The patent that was filed in 1937 to create this process. And DuPont, of course, became a household name for a generation of Americans. And as we can see here, kind of intimate or intimated in this picture is what happened with that nylon was a whole fashion run, no pun intended, on stockings. And what we discovered with the students as we were exploring this topic was in 1940, in one day, 400,000 pairs of nylons were sold because of the craze over this ability to basically decorate and change the color and basically the appearance of your clothing. So the young ladies basically just drove the demand for this. And over the course of just a few years, up until World War II, really where the U.S. Army had to pull away the nylon production industry to make, believe it or not, parachute cords, stockings were selling in the millions. And so this has set the tone back in the 1940s to what we would even call fast fashion today. The fact that you can walk into a store and buy a shirt or a pair of pants that's only going to cost $2 or $3 or $5 because the majority of that material is not made from a naturally grown cotton that took time and labor to produce, but really it could be manufactured in a factory from two solutions being added together. So we have future aspiring designers and folks very interested in their fashion, as you can imagine young men and young women are. And so to understand that just chemical combinations are really producing the base material for the clothing that they treasure and love is really quite eye-opening. And the kind of dark side to this is the suppliers of those base materials, believe it or not, are your petrochemical companies. So the starting material for those two solutions that were poured in are often products that are the result of the refining of crude oil. So the excess little extracts after the diesel is pulled off, after the fuels pulled off for vehicles, then you have these other chemicals, and the petrochemical industry has found a way to monetize that into clothing. And so there's a little bit of a debate there that our students then engage in, and whether they should go buy secondhand clothing, whether they should aim for all natural clothing, or continue to kind of feed the pockets of the petrochemical industries who are supplying the base material, again, for all the fashion industries. And you can imagine the kind of discussions that come out for our students. Right, Harvey has a question about hydrocarbons, and that's exactly right. These polymers come from those hydrocarbons. So that right there is a little kind of view into the student experience as we engage with them when they first come to us, maybe not so interested in being a scientist, or kind of having an aversion to it for whatever reason. We give them multiple entry points, and those multiple entry points then allow them to make a decision for themselves as to how this journey is going to continue. And so in the next 5 or 6 minutes, I'm just going to walk through a few then initiatives that we had on our campus to support these students when they say, okay, I'm interested in this first chemistry class. How do we go from here? I basically took advantage of, and I'd like to just commend Angelica Stacy. She was my research advisor at UC Berkeley here. We built a coalition, including faculty at Sonoma State and Diablo Valley College, to develop curriculum to help students see themselves as STEM thinkers and learners. And we noticed that we would run into students who were basically being held down or held back by stereotypes about what being brilliant in science meant. And there was a who counts kind of continuum that was discovered in the research, that Asians, males, whites, females, Black and brown students kind of were the hierarchy of perceived ability. And I think you all for sure have experienced a male-female kind of whether it's a discrimination or a distinguishing that society has placed on your perceived ability to be in these fields, right? And so that who counts narrative actually we'll see is problematic and troublesome. And then there's also a what counts as being a scientist, and it's often attributed to you were born with some innate talent that makes you good at being science. Good at science, knowing lots of information, being able to speak it quickly and correctly, right, is something that often gets attributed. And so what this ends up happening is the school science that's taught in the classroom values the who counts and the what counts. It values a body of known info and problem-solving skills that were developed quickly and correctly. It emphasizes memorizing content. It's a very static type of science. You achieve a certain type of a level, and then you get moved on to the next level, and it's very individualized. And what we've realized that science in practice is really around practicing those bold guesses. Develop explanatory models. Look at some data you've never seen before and try to pull out from it a hypothesis. So it's iterative, it's messy, it's creative, it involves collective sense making, and also includes, there's a lot of potential here for being more inclusive and pulling in what other cultures understand science to mean. And so our team ended up developing curriculum that I'll just summarize as group-worthy data tasks, where students do science together, they benefit from thinking together, and there's many more entry points for students to experience themselves as being smart at science or good at science. And so this idea of, well, you don't know, but let's put in a guess. And I'll just show, I'm going to kind of a sample type of task would be to ask why some solutions conduct electricity and others not, and give students multiple entry points, the ability to do the experiment, the ability to look at some representations, the ability to work a little bit with mathematical quantities and filling out a table, bringing in your data, organizing it, communicating your organization, and working together actually helped us to achieve a goal of changing this narrative of who's good at science. So I'm going to actually jump forward to one of our scholars, and this is Isela Sosa, who actually didn't grow up in this country, but is as a first a parent, student parent, and now a working parent of two. This quote: "When I was in my country, I did not want to go to school because I believed that I was a bad student." We can see where that could come from, right? From a perceived ability. But at COM, I'm discovering that I'm actually a good student and I can still dream for a better future, even though I'm not in my 20s anymore and I have kids I need to provide for. And so a second initiative we did through this project was to invest in the STEM infrastructure at the College of Marin. And some of you have had that privilege of being down there in the STEM Center, where this little empty room was renovated in July of 2019. And a nod to Ray Kinsella in the Field of Dreams: if you build it, they will come. And this was a poster presentation that was just conducted this past September. And you can see it's full of research conducted by various of our own students who were able to do summer research and then come back and share their experiences in doing it. So I just wanted to kind of highlight that in our STEM Center, there's the opportunity to build community, to connect with other students on a weekly and a casual basis, to bring in speakers who are able to share their research with us and give students multiple entry points. And where that has led to today is, I'll just jump over to this slide, is we received funding from the Chancellor's Office this past spring to launch the MESA program at the College of Marin. MESA stands for Math, Engineering, Science Achievement, with the particular goal of supporting STEM students transfer to a four-year university. We were able to hire a MESA director this summer, Nicole McIntyre. She originally was going to join this presentation with me, and unfortunately, fortunately, she's leading a group of students to tour Sonoma State right now. So we're actually, I've included her info. You're welcome to contact her, but she shared a few stats here that currently we're serving 61 College of Marin students, 37 who meet some specific MESA criteria, and 24 additional friends of MESA. And you can see we are reaching a group of students that we wouldn't have necessarily have reached before without the support through the MESA program. So those needing need-based financial aid, students of color who are underrepresented in many of the STEM fields. And maybe I'll just finish up with a few of the activities. We were able to do some outreach activities through an egg drop challenge to see who could preserve an egg as that's dropped. We're able to do a power up event where we're able to reach a number of students with hands-on demonstrations, give them an opportunity to see different models. This was actually built by our students during the summer. And then the MESA program has collaborated with the Buck Institute to bring in representative scientists to talk about their experience. And here's a panel with over 40 students and staff faculty who attended that event just last month. And then finally, they've been able to go to conferences They've been able to attend transfer days, UC Davis. I also mentioned the one at Sonoma State that's going on right now, and there's many more active partnerships. So I'll just kind of close at looking forward. MESA is reaching out to middle and high schools. There's cohorting taking place, and we're actively thinking of how to partner and bring in campus and community advisory councils, as well as structured mentoring. And so we know the ESCOM Connects has been mentioned to us with Curiosity, and we're with Curiosity, we're considering how to best bridge some of our students with possible mentors. And then you can see NASA is always on our radar. That really has the sparkle that attracts students for an interest in continuing with us. So maybe with that, I'll bring us to this conclusion. Thank you for your attention. It's been really a joy to kind of share this trajectory with you all. And I would like to just maybe open it up for questions. I know some of you might have some questions of things either that was shared today or something you had thought of leading into this conversation. I'm currently, again, yeah, maybe I'll pause right there. Thank you.
Yeah, Paul, thank you. Thank you so much. It's great to have a science class. And I think that takes us back to at the beginning of, isn't it great that we have access to professors at the college so that we all get an opportunity to experience what the students get to experience by having excellent faculty. One quick question, and we'll look for other questions. Do you think by STEM, by combining science, technology, engineering, and math into a word like STEM, it further invites collaboration and brings students into studying science that they might have when they see them all partnered together, in the word STEM? I mean, what has that done for the field?
Oh, tremendously. We have quotes from students that they felt very isolated. They would take a class and not recognize that there's someone just like them in that class. And through the STEM center and then the MESA space, they were able to walk in and recognize, wow, you're my future best friend. I can just share a little example. I had two geology students who, and that's kind of a rare major on our campus, to major in geology. They were both first-gen students. They were both part of the MESA program, but they were in different chemistry classes, and so they weren't aware of each other. And through MESA, they were able to meet, and after that first introduction, we literally, like peas in the pod, we could not separate those two guys because they were just so like-minded, and we can see that trajectory staying with them and being the foundation for their science learning. Who knows, maybe they'll transfer together and end up at the same UC. And so that to us is crucial in being a successful STEM student, is not just the material, but learning how to collaborate and benefit from working with others, because none of us are all inclusive. But if we can recognize the strengths we bring and benefit from the strengths that others bring, I could go on and on with the stories of how our students have changed their trajectories through this type of collaboration.
That's just great, and we'll have to have you back because I'd love to hear more. Lois, it looks like you have a question.
Yes, I do. I was wondering what you think of the gifted and talented programs that are available to children in elementary school. What is your opinion of that?
For sure. So I had both the benefit of being in a public school and participating in a gifted and talented program, and then being in a public school that didn't have a program like that. And there is a natural curiosity that students have about learning. And I'm going to say something that might provoke some response, but there's a gendered curiosity that unfortunately doesn't get promoted in middle school. And what I mean by that is I see a lot of young women who are in that 5th, 6th, 7th grade level who are more advanced than their male peers in their scientific ability. But because of this valuation of being quick and correct, you see the boys, they'll raise their hand and blurt out something foolish because they don't even care. They don't even know what's in their head. They just kind of blurt it, and they get feedback from the teacher. That feedback, right, that bold guess, helped them modify their thinking. Whereas the young lady who maybe had an even better idea, but was a little bit hesitant or not as quick to just raise her hand, as a result, doesn't get that feedback, the positive correction or reinforcement, and we see this cycle just propagate. And so I would love to see gifted and talented programs in whatever domain acknowledge that there are gender and also cultural and socioeconomic differences, and open up avenues for those students to have those opportunities. So I just kind of used a broad brush example of a male and female junior high classroom, but you can imagine how that type of interaction of getting more feedback, promoting your curiosity and interest, is something that isn't even-handed in our classrooms today.
Oh, good point. We have another question. A.T. Lynn? Go ahead.
Yes. Yes. Oh, Paul, there you are.
Yeah.
Shifting around. Thank you. This was fascinating, and I was already eager to hear what you had to say, because I worked for 20 years in the construction management engineering industry.
Cool.
And my degrees are in a different area, but I would love to just be available for questions about what is life. And, you know, of course, the gender split's pretty obvious, but I'd love to just dissolve that, because it is dissolvable. And I would love to talk with the kids that you have or the students at any age, and just see how I can fit into your STEM MESA program.
Oh, great.
Thank you for that enthusiasm. Yeah, we're always looking. During the pandemic, we actually just tried to bring in speakers, right? Because it was very hard to do anything face to face. Now we have the opportunity to have little like brown bags during the lunch hour. We just kind of fill a space with an expert and allow folks just to bounce ideas off of and have questions. So I've been pondering how the ESCOM Connects program would work, and your suggestion is actually a good one, just to say, let's put you all in the same space with folks who might be in that same kind of trajectory or same kind of experience, and ask me anything, right?
Yeah, no, great. And listen, we must stay in touch, because I think ESCOM Connects and ESCOM as an organization would love to have more access to your classes, to your ideas, to your brown bags, to your students. I'm with ESCOM Connects, and for instance, I got an email the other day from a doctor who's one of our members saying, how can I help? I'm retired, but I want to stay in the field. Where can I help your students? So we often, you know, many of our members are like-minded in that we'd love to stay involved, and I love the science class. I haven't had one for a long time. You know, I'm noticing it's already 11, and I certainly don't want to take advantage of your time, Paul. This has been wonderful. Is there any other quick question that anyone would like to throw out before we thank Paul and wish you all a good day? Harvey?
Yeah, well, I just wanted to, I did put in the chat there, Paul, but do you have any bold guest projects that you're personally working on?
That's really, I like that. Thanks for setting me up. I'll just, a little personal anecdote. My high school teacher, I didn't find this out till about 10 years later, won the National Chemistry Teacher of the Year award. And we just thought like she was making chemistry really great for us. Turns out she was the best in the country at that time happening to do this at my little small public high school. And so I would want to just do a quick little poll. How many of you had a good chemistry teacher in your mind? Just show of hands. Because we often associate our affinity or our interest in chemistry specifically for some reason with how that teacher was able to bring that topic to us. And so that's a little project that I've been looking at, thinking in the future, how our representation can increase of more female or underrepresented faculty to have more contact points and models and patterns for our young learners. Doesn't necessarily have to be a faculty member, right? It could just be someone who's mentoring them or talking to them about the trajectory that gives them an encouragement. You did it as a mom or as a later in life student, I could do that too. So that's kind of my a future project I'm thinking about, how to increase representation in our STEM instructors, staff, and faculty.
Well, we've got a lot to talk about. ESCOM loves you already, Paul, and we've got to brainstorm ideas together. Listen, thank you so much for taking the time. It's been a really wonderful, informative, inspiring talk. And we will obviously be in touch with you as time goes on. And to all of you who attended, love to see you. And it was great to have you with us. And there's more and more spotlight programs coming starting in 2024. So stay tuned for some announcements of other programs. But thank you. Have a great day, a wonderful weekend, a beautiful Thanksgiving, and we'll see you the next time. Thanks so much, Paul.
Yes, thank you. And this will be is recorded, so we will post it.
Great. Thank you.
Awesome.
Bye-bye.
Take care.